Hello everyone, this is Son of Winter. Today I'll be presenting the next lecture on the gaseous state. Here are the content and the assessment objective for this topic. We are focusing on the ideal gas law in solving many questions for this topic. Now, introduction. Gases are made up of particles that are separated by large distances because there are weak intermolecular forces between the particles. And we also understand that particles are always in constant random motion. Now, this constant motion or movement in a container will result in constant collisions with the walls of the container, and it gives rise to pressure. And the gas particles are always moving because they possess this energy called kinetic energy. And this kinetic energy is related to temperature. So with higher temperature, the kinetic energy of particles will increase. So these are the physical properties that characterize gaseous state. Number one, gases do not have a fixed shape and volume. They assume the volume and shape of the container that contain them. Gases are highly compressible and the volume will change greatly with changes in pressure. Gases exert pressure evenly in all directions. They mix evenly and completely when confined to the same container. Gases compared to liquids or solid of the same substance will have much lower densities. They are also poor heat conductors or good insulators. So the physical properties or the behavior of a sample of gas can be described completely by four measurable macroscopic properties, namely pressure, volume, temperature, and amount of gas in terms of moles. Through a series of experimental studies, the relationship between these four variables are expressed in the gas law like Boyles Law, Charles' Law, etc. So in Boyles Law, it states that for a fixed mass of gas at constant temperature, the volume is inversely proportional to the pressure. That means PV is constant. So the effect of changing pressure on the volume for this fixed mass of gas can be deduced using P1V1 equal to P2V2. That only is true when the temperature is constant. Okay, so the product of pressure and volume will be constant. So if you change the pressure, the volume will change accordingly. Now let's look at a sample question to understand how the equation can be applied. The sample of a gas has a pressure of 2 atmospheric pressure and a volume of 45 dm3. Find its pressure if it is compressed to 10 dm3 at constant temperature. Note, the temperature is constant for the same sample of gas. So we can directly use Boyles' law to help us solve the question. P1V1 equals to P2V2. So to find the pressure at 10 dm3, we take P2 equals to P1 times V1 divided by V2, which is the volume of the gas at the required pressure to be determined. So the pressure initially was 2 atm. The volume was 45 dm3. You do not need to do any conversion. We just express the answer in terms of the units given. So 2 times 45 divided by 10 will give us 9 atm. So the pressure when volume is 10 dm3 will be 9 atmospheric pressure. Charles' law. Now, Charles' law states that for a fixed mass of gas at constant pressure, the volume is directly proportional to its absolute temperature, which is in Kelvin. So at constant P, V and T are directly proportional, which means that V over T should be constant. So the effect of changing pressure of the volume for this fixed mass of gas at constant P can be deduced using V1 over T1 equals to V2 over T2. So the ratio of volume to temperature is constant. That is provided the pressure is constant as well. Now let's look at this example to understand how the equation can be applied using Charles' law. A sample of gaseous argon maintained at constant pressure is found to have a volume of 10.5 meter cube at 25 degrees Celsius. So if you heat the system to 250 degrees Celsius, what is the resulting volume? Note that the pressure is constant as stated in the question, constant pressure. Now, so V1 is 10.5 meter cube, V2 is the unknown. T1, remember, this temperature has to be in absolute temperature, Kelvin. So you need to convert 25 to Kelvin plus 273 to give you 298 Kelvin. And the temperature when the system was heated to was 250 plus 273 to give us 523 Kelvin. So applying Charles' law, V1 over T1 equal V2 over T2, we make V2 the subject of the equation, and we will have 10.5 divided by 298, which is the initial conditions, multiplied by the new temperature to give us the volume, which is 18.4. So we can see that the volume increases with increases in temperature, and the increase is directly proportional. Now, move on to the next law, Gale law. It states that for a fixed mass of gas at constant volume, the pressure is directly proportional to its absolute temperature, which is measured in Kelvin. So at constant V, P and T should be directly proportional. This means that P over T will be constant. So the effect of changing pressure on the pressure for this fixed mass of gas at constant V can be deduced using P1 over T1 equals to P2 over T2. The last law to use before we deduce ideal gas law will be Avogadro law. So Avogadro hypothesis states that at constant T and P, gases of the same volume contain the same number of particles. This means that 1 mole of any gas will occupy the same volume as another gas at the same temperature and pressure. The volume occupied by 1 mole of any gas is called the molar gas volume. Now, we need to remember this very well. At STP, which is the standard temperature pressure, the volume was 22.7 dm cube per mole. So the condition at standard temperature pressure will be 10 to the power of 5 Pascal, which is equivalent to 1 bar, and 0 degrees Celsius, which is 273 Kelvin. Okay, the data can be found in your data booklet in case you forget the volume, the temperature, and pressure, okay, at standard temperature pressure. At room temperature pressure, which you learn at O level, is 24 dm cube per mole. But the condition will be different from STP. RTP is at 1 atm, not 1 bar, which is at 101325 Pascal. So it's not the same as this, all right? And the temperature is at 20 degrees Celsius. So this 20 degrees Celsius is the room temperature, not 25, okay? So it's set at 293 Kelvin. So this means that 1 mole of nitrogen gas occupies the same volume as 1 mole of oxygen gas under the same temperature and pressure. Under RTP, 1 mole of any gas should occupy 24 dm cube based on Avogadro law. Now, stemming from Avogadro hypothesis, Avogadro law states that for a gas at constant temperature and pressure, the volume should be directly proportional to the number of moles. So at constant T and P, V and N should be directly proportional. So if you shift the variable, you should get V1 over N1 equal to V2 over N2, where V over N is a constant. Now, let's look at this example to understand how the equation can be applied to solve question. Now, we have 4 grams of methane, which occupy a volume of 6.25 dm cube at a particular temperature and pressure. Find the volume of the same mass of hydrogen under the same conditions. So we can calculate the number of moles of methane to be 4 grams divided by 16, which is the molar mass of methane, to give us 0.25 mole. And at this amount of methane, we have a volume of 6.25 dm cube. Now, when the volume changes, all right, the number of moles changes. So at this new number of moles, it will be 4 grams divided by 2. I'm sorry, comparing methane with hydrogen, we are comparing different gases. So if they are different gases, but they are at the same temperature and pressure, we can directly relate their mole to volume actually. Because based on Avogadro law, the same mole of gas should occupy the same volume, right? So given 4 grams of hydrogen, because they mentioned the mass of hydrogen is of the same mass, so we divide by the molar mass of hydrogen, we will get 2 mole. And then we apply Avogadro law, V1 over N1 equal to V2 over N2. You make V2 the subject of the equation. You have N2 over N1 times V1, which is 2 divided by 0.25 multiplied by 6.25. So the volume of hydrogen, which have a larger number of moles, should have a much larger volume because the relationship between N and V is directly proportional. So it's 50 dm³. Now looking at ideal gas equation, all right, the 4 gas laws are all interrelated. So putting all the gas laws together, we will develop this equation called ideal gas equation. So we introduce a new constant by putting them together. This constant R is the molar gas constant. Now, depending on the units of pressure and volume, the molar gas constant will have different values. So the commonly used values will be 8.31 joules per Kelvin per mole. Sometimes we use in terms of atmospheric pressure, volume, and Kelvin and mole, then it will be 0.0821 atm dm³ per Kelvin per mole. So it depends on what are the units used in the equation. So the common SI unit used will be this 8.31, which you can find in the data booklet, okay? But it will be faster if you remember this so that you can apply to the equation very quickly. Now, it will be very useful to know some of the conversions, like 1 dm³ is equivalent to 1000 cm³. If you want to convert dm³ to meter cube, you divide by 1000 to obtain 10 to the power negative 3, because dm is of a smaller unit than meter. And if you want to convert cm³ to meter cube, you need to divide by 10 to the power of 6, which is 10 to the power of negative 6. Okay, because cm to meter is divided by 100, but because we are talking about volume to cube, so it's 100 times 100 times 100. Then for 1 atm is the same as 100,000 100,001 325 Pascal, and this is the conversion for temperature between Kelvin and degree Celsius. Now, so here are some examples that you can try, okay, at your own time. Calculate the volume of nitrogen gas with a volume of 200 cm³ at a temperature of 100 degrees Celsius and pressure of 10 atm. So the volume was 200 cm³. You need to convert to meter cube. And then the temperature convert to Kelvin. Pressure convert to Pascal. So everything convert to SI unit, which is easier. Apply the equation PV equals to nRT. And then amount means number of moles. Just remember that. Amount means number of moles. So you shift everything to make N the subject of the equation, and you will get 0.0654 mole. Now, another example to reinforce the understanding, what mass of zinc is required to produce 2 dm³ of hydrogen at 15 degrees Celsius and 50 kilopascal by reaction with excess acid. Now, in this question, we will work backward. We will find out the mole of hydrogen and then work out the mole of zinc and then the mass of zinc required. So we work backward from hydrogen. Now, hydrogen has a volume of 2 dm³. It is not the SI unit. So we will need to convert this to meter cube by dividing by 1000, which is 2 times 10 to the power of negative 3. Degrees Celsius 15 will be converted to Kelvin. Pascal, no, they are given you kilopascal and not Pascal. So 50 kilopascal multiplied by 10 to power of 3, you'll get 5 times 10 to the power of 4. So this times 1000 to obtain this. And M is the number of moles of hydrogen. So apply this equation, substitute the relevant values. So N equals to PV over RT. So you just shift the equation to make N the subject of the equation. And then you will have 0.04178 mole. So use this to work backward to find the mass of zinc. So the mass of zinc will be calculated as the number of moles of zinc, which is actually the same as hydrogen given the mole ratio. And then you will get 2.73 grams. Now let's look at a partial question. Okay, you can try this question at your own time before we check the answer. Now, in this question, you are given a mass of ideal gas which occupies a volume V and exert a pressure P at 27 degrees Celsius. So at which temperature will the same mass of ideal gas occupy the same volume and exert a pressure? So what is the strategy in doing this question? First of all, you have to know what are the variables given. Now, you are given a given mass of ideal gas, so the mass is constant, and it occupies a certain volume V and exert a pressure. So they are saying that for this mass of ideal gas, the volume remains constant. So you will use the relationship between P and T. P is directly proportional to T. Because what changes in this question will be the pressure and the temperature, while volume was kept constant. So you take P1 over T1 equals to P2 over T2, and you make T2 the subject of the formula. You will get P2 times T1 over P1. And the new pressure is 2P, which means it is 2 times the original pressure. And this is the original pressure. So you can actually cancel off using algebra, the common algebraic term. Then you have 2 times the temperature, 27 plus 273, you obtain 600 Kelvin, which is T. Now, another example, you can look at this question before solving and check the answer. So we have 1 dm cube of balloon filled with helium gas released at sea level when the temperature is 29 degrees Celsius and the pressure at that point will be 1 atm. So what will be its volume when it reaches a height where the temperature becomes 27 degrees Celsius, which is lower, and the pressure is also reduced to 0.98 atm. So please take note that the helium gas in the balloon remain in the balloon. So that is the important assumption. Okay, we don't assume that the gas leak out from the balloon, but remain in the balloon. Okay, if not, we cannot use the equation to solve the question. Okay, so the amount of helium gas should be constant. So N in the equation PV equal nRT should be constant. Now, the initial pressure is 1 atm and the final pressure at a certain height will be 0.98 atm. The volume of the balloon will be 1, but you should understand that with decrease in pressure, what will happen to the volume? All right, it should actually increase. Yes, with lesser pressure adding on the balloon should expand. Okay, and we also convert the temperature to Kelvin so that we can actually use it in the equation correctly. So since N is constant, PV over T is a constant. So we just use the expression P1 V1 over T1 equal P2 V2 over T2. Then we make V2 the subject of the equation since this is what we are trying to determine. And then you just substitute the relevant values and you will get 1.01 dm cube. Try to leave your answer in 3C for all chemistry questions. Now, so you understand that through a rearrangement of the ideal gas equation as shown above, we can actually solve a lot of questions. But another important feature of the ideal gas equation would be determine the molar mass of a gas. We can do that by looking at this. So we can actually obtain an expression so that we can determine the molar mass of the gas. So using ideal gas equation, PV equal nRT, PV equals to M over molar mass. So the number of moles is calculated as m over m times RT. All right, so rearranging the equation, we will have mRT over TB. All right, so note that molar mass has the same numerical value as the relative molecular mass. So it is important to note that while m has the unit of gram per mole, mR is dimensionless with no units. Okay, mR is dimensionless, but molar mass has a units. So let's look at an example to further understand how this equation can be applied. A large flask is evacuated and found to weigh 134.6 grams. It is then filled to a pressure of 98 kilopascal at 31 degrees Celsius with a gas of unknown molar mass and then reweighed. So its mass is now 137.5 grams. Okay, now the evacuated flask is then filled with water and again weighed, and the mass become 1067.9 grams. Now let's assume that this gas behave ideally. Okay, so what is the molar mass of this unknown gas? Okay, and also an additional information is the density of water at 31 degrees Celsius is 0.997 grams per cm3. So how do we approach this question? How should we start? All right, so to find the molar mass, we must first look at what is given in the question. All right, so we first find out the volume, because the ideal gas law has this quantity volume. But in the question, they've given you density, all right, and given you mass. So I will use mass divided by density to determine the volume, all right? So let's look at this expression first. So to find the volume so that we can use it in the equation, right? The mass, the final mass is 1067.9 grams. The initial mass was 134.6. Okay, so this is the difference in the mass. And then you divide this by the density, we will obtain 936.1 cm3. Okay, which will be 9.361 times 10 to the power negative 4 meter cube. Now, so this is the volume, and we also have the pressure. So the pressure given was 98 kilopascal. So we just multiply by 1000 to obtain the pressure in pascal, since the pressure was given in kilopascal. And then we convert temperature to Kelvin as usual. Applying the equation PV equal nRT, we're going to use this equation very frequently. So substitute P as this, substitute V as this, equals to N, which is what we're going to determine. R is 8.31. We need to convert to meter cube because we're going to use R as 8.31. So the units has to be consistent with what the constant is. All right. Then multiply by the temperature in Kelvin, and we will have the number of moles calculated at 0.03631 mole. So using this, okay, we find out what is the molar mass. Molar mass is mass divided by number of moles, but we need to know the mass. So the mass of the gas, all right, was 137.5. So it was a difference of this and this, because the large flask was first weighed to be 134.6. So that was the mass without the gas added. And after the gas was filled in the flask, the mass was weighed to be 137.5. So the difference in this will be the mass of the gas. Okay, but for the water just now, right, we use the water to help us to get the gas because the volume occupied by the water and the gas should be the same. Okay, so we are making use of the water, okay, which occupy the same volume to help us determine the volume of gas occupied. So because we know the density of water, but we may not know the density of the gas. All right. So after you get 2.9 gram, you divide by the number of moles of the gas. Okay. So the molar mass was 79.9 gram per mole. Okay. Now, another example is this. You have a compound X as a volatile liquid. In order to determine the relative molecular mass of X, an experiment involving the apparatus as shown below was used. All right, so you have a granulated gas syringe here, and you have a thermometer. Then the experimental results are shown below. So the mass of the hypothermic syringe containing X. So before injection, the mass was measured to be 20.476 gram. After injection into the gas syringe, the mass was 20.252. So there was a loss of mass because the X was released. Okay, the initial reading was found to be 1.4. Final reading is 96.8. So the difference in the volume, okay, will give you the volume of the gas. The temperature of the heating jacket was 99.6 degrees Celsius and the atmospheric pressure 100 kilopascal. Now, how do you solve this question? A few steps. First of all, X is a volatile liquid, so it easily vaporizes. So because it easily vaporizes, the increase in the volume in the gas syringe is actually just due to X. That is the assumption. Okay, so the gas, right, will cause the increase in volume, and it is just due to the gas. So with that understanding, we can calculate this data. So the mass difference will be 20.476 minus 20.252 because you release the gas. So there's a drop in mass. And the drop in mass because the gas is released. So this is the mass of the gas, 0.224, when you take the difference of the mass before and after the injection. The pressure was taken to be this 100 kilopascal. And you just convert it to Pascal because we need to make the units consistent in SI unit. Temperature have to be converted to Kelvin. 99.6 plus 273, quite straightforward. The volume, okay, just assume that because it is a volatile liquid, so the expansion is plainly due to X. So the difference in volume, 96.8 minus 1.4, will give us the volume of the gas. And convert this to meter cube, or cubic meter rather. And then from there, you use ideal gas equation, and then we shift the molar mass to become the subject of the equation to solve the question. Just substitute the relevant values in, we will get 72.7 gram per mole. Since the question was asking for MR, we have a separate statement that says MR of X is 72.7. We cannot leave this as the final answer because the question specifies MR of X in the question. Now, how about determining the density of a gas? So we can rearrange the ideal gas equation to give an expression involving the density of gas. So we know that M over M is equal to number of moles, right? And we also understand that we can shift the V over to make M divided by V. So this will become density. And then the density is equivalent to pressure times the molar mass over RT. So this equates to density, and you shift the rest to make this the subject of the equation. Now let's look at this example. You can pause the video before we run through the answer. You have a sample of organic molecule of molar mass vaporized in a gas syringe and occupies a certain volume, a certain temperature, and certain pressure. So you just need to shift the variables based on this equation. So your density will be the pressure multiplied by the molar mass over RT. So what is the density of the compound? Okay, so if you shift the variables, you will get this. But if you look at the choices, which is more likely to be the answer? we notice that R is actually not given. Do you realize that? So if R is not given, we can derive by using VTP of 1 mole of gas at room temperature condition. Because since you don't give me R, then I will find an expression to feed other variables in. So given room conditions, we have temperature at 283 Kelvin. So at this temperature, at room temperature conditions, we should have a volume of 24,000 cm3 and a pressure at 1 atm. And using that, we have volume times pressure. We have 24,000 divided by the number of moles, assuming it's 1 mole, and then times 293. It might be 1 mole because molar volume refers to 1 mole. 24 dm3, 1 mole of gas occupied 24 dm3. And then you will get this. And substitute R expression into equation 1 here, you will find the answer to be B. So this is the expression. Now, next, how do we sketch graph using ideal gas equation? So we can actually generate graphical plots for a fixed amount of ideal gas. So these are some basic knowledge on graph plotting. So y equal to kx, where the graph cuts through the origin. If it doesn't, it's kx plus c. C refers to the y-intercept. If you have something like this is inversely proportional relationship between y and x, is y equal k over x. Or if something like this, y equal to c. So how should we approach such questions? So we have graph to sketch. So we have P against V for fixed mass of gas at constant T using Boyles Law. So to manipulate the ideal gas equation, PV equal nRT. So we have P inversely proportional to V. So in this case, the graph is of type 3. Y equals to K over X. What if we have this? PV against P for a fixed mass of gas at 2 constant temperature. Okay, so PV equal nRT. So the graph is of type 4. All right, because in this case, when we want to plot PV against P, all right, at a constant temperature, obviously it will be a constant because the expression on the right is all constant. Okay, and if we have a temperature that is higher, then obviously the constant will be of greater value if T1 is greater than T2. If we have P against 1 over V at a fixed mass of gas at 2 constant temperature where T1 is greater than T2, so let's look at the equation PV nRT. We shift the V over to make P the subject of the equation, and then you take out nRT, assuming that the temperature is constant. You notice that P and 1 over V are actually directly proportional. So it will be a straight line graph that cuts through the origin. So it is something similar to type 1, y equal to kx, where it's a straight line that passes through the origin. So if T1 is greater than T2, the graph at T1 should have a steeper gradient. Yes, meaning the constant is greater. So the gradient, which is the constant, should be of higher value and show a steeper gradient graph. Now, if we have V against T over against T, sorry, this is Kelvin, for a fixed mass of gas at constant P, so P against T, then it also should be a straight line graph that cuts through the origin. In this case, N over R over P will be a constant, which is the gradient of the graph. And you can actually determine the gradient, which should be equivalent to NR over P. What if you have V against T for a fixed mass of gas at 2 constant pressure? Now, so in this case, the temperature will be changing. So it's P against T. So V against T, where P is constant, but T, all right, is in degrees Celsius. But to relate them, the temperature must be in Kelvin. So you make sure that you plus 273 here before you construct the equation to relate V and T. So this is a bit mathematical. So N and R are constant. So V is directly proportional to T plus 273 at a particular pressure. Yeah, something like that. Because you can actually just combine them and realize that, oh, V and T plus 273 is constant. Straight line graph that cut through the origin. So this graph is of type 2, not type 1, where you have a y-intercept because of the temperature that is measured in Kelvin, not degrees Celsius. So it will cut through the origin. Sorry, it will not cut through the origin with a y-intercept of nr over p times 273. So this is the y-intercept. Y equal ms plus c. So this is c. So this should be the intercept. The gradient of the graph should be nr over p. Yeah. So if you have P1 greater than P2, it should be a graph of, because pressure is in the denominator. So the larger the value of P, the smaller the gradient. All right. So P1 graph should show a gradient that is less steep. Okay. When will this V be 0? Why is it minus 273 here? Because when you substitute T equals to minus 273 here, the whole expression here becomes 0, which explains why these two graphs cuts the x-axis at minus 273 because of this equation. You have to sub into C clearly. Now let's look at one example to reinforce the understanding. First of all, the question asks you to sketch graph of P over density against temperature for n moles of ideal gas where, yeah. Then we have temperature as Kelvin and small t as temperature in degrees Celsius. But they want in degrees Celsius, so you have to do the conversion. So PV equals to N over M times RT. You shift the equation to make, okay, so this M, you shift the V, M over V, then become density, and then you shift the density over, P over density equals to R, bracket T plus 273. Make sure you have to convert to degrees Celsius and not keep it as Kelvin, because that's what the question wants. Divide by the molar mass. And then you just split up this equation to form the y equal ms plus c graph. You should get r over m plus r over m 273. Okay, then it should be a straight line graph that does not pass through origin, similar to the earlier graph. Now, next, the kinetic theory of gases is a mathematical model that studies the behavior of gas. It explains the macroscopic properties like pressure, volume, temperature, and number of moles in terms of its molecular behavior. So in reality, right, we need to understand that ideal gas don't exist. It is just a hypothetical gas that allows us to understand how real gas behave. We need to understand the assumptions that apply to ideal gas. Now, so these are some assumptions applied to ideal gas. So when these assumptions are met, then the gas will behave like the ideal gas. Okay, the ideal gas consists of particles of negligible volume. So the size of the gas particles is negligible compared to the volume of the container. Okay, so I think this is not possible. All right, it means that the gas particles is so small. Okay, now the gas particle exert negligible attractive force on another, which is not possible. But in ideal gas, we have to assume that the gas particles are in constant random motion. They collide one another and with the walls of the container. And between collisions, they move in straight lines. Collisions between gas particles are perfectly elastic. There's no loss of overall kinetic energy upon collision, though kinetic energy still can be transferred between colliding particles. The average kinetic energy is constant at constant temperature, where the average kinetic energy will be proportional to the absolute temperature. So at the same temperature, all gases have the same average Ke. So remember these 5 assumptions. They will just ask you some of the assumptions that will be applied to ideal gas. Now, Ideal gas is one that obeys the ideal gas equation under all conditions of pressure and volume. So an ideal gas is assumed to be one where the gas particles have negligible volume or exert negligible attractive force on one another, or rather N. Now, as mentioned previously, ideal gas do not exist. All real gases will deviate from ideal gas equation because they cannot follow two assumptions entirely. Number one, in real gas, the gas particles have finite volume and size, which violates assumption one. And there are attractive forces between the gas particles, which violates assumption two also. Now, so in order for real gas to approach ideality, these are the two conditions. Number one, low pressure, and number two, high temperature. So how do you explain how low pressure and high temperature allows the gas to approach ideality? Now, at low pressure, the gas particles are very far apart, so they can be considered to have negligible volume compared to the volume of the container. And also because they're so far apart, right, due to low pressure, we can neglect the intermolecular attractive forces. As for high temperature, because the molecules have high kinetic energy, so they can overcome the intermolecular attractive forces, which means that these attractive forces are negligible. So to approach ideal behavior, the conditions are low pressure and high temperature. So conversely, a real gas deviate most from ideality at very high pressure and under low temperature. So the opposite will happen. So with high pressure, the gas particles are very much closer together and the gas occupy a smaller volume because they are so close together. And the gas particles cannot be considered to have negligible volume compared to the volume of the container. In addition, because they are closely packed due to high pressure, the intermolecular attractive forces are significant. While at low temperature, the gas molecules have less kinetic energy and this intermolecular attractive force becomes significant. So this is a summary of what we have covered. Then if you compare between ideal gas and a real gas, so these are the difference. For ideal gas, the molecules have negligible volume, while a real gas have a finite size and volume. In ideal gas, there are no forces of attraction between molecules, but in real gas, there are forces of attraction, and the forces of attraction of some gases are greater than others. Like ammonia molecules, there are greater attractive force between them due to hydrogen bonding than between hydrogen molecules, which is just ID-ID interactions. Now, when the molecules collide in ideal gas, the collision is elastic. So the molecule just bounce apart with no loss in kinetic energy. But in the real gas, this is not the case. The collision may not be elastic. It will not be elastic, actually. Now, next one. For ideal gas, right, it obeys the gas law and the ideal gas equation perfectly well, but in real gas, don't do that. At low pressure, the molecules are far apart. So these are the conditions for real gas to approach ideality. So they have to be far apart at low pressure so that the volume they occupy is negligible compared to the volume of the container, and the intermolecular forces of attraction will be negligible as the particles are far apart. And at high temperature, the gas particles have large kinetic energy to overcome attractive force. So these intermolecular forces of attraction become insignificant. So for ideal gas, we use PV equal nRT, and we can just use the equation directly and sketch any graph that is required. However, real gas will deviate from ideal gas behavior. So what are the factors that will affect this? Will be the type and magnitude of intermolecular force, as well as the size of the gas particle. So let's look at this. We plot a graph of PV over RT against pressure for 1 mole of nitrogen gas at minus 25 degrees Celsius. And we see something. So the curve shown on the right for 1 mole of nitrogen gas is actually typical for most real gases. So it will decrease below the ideal value at high pressure. So you can see that there is a great deviation as the pressure increases. Okay, but when the pressure is lower, okay, it will be closer to the ideal gas. Okay, so you can see that it decreases below the ideal value at moderately high pressure and then rises above it as pressure increases further. The shape arises from 2 overlapping effects. 1, the gas molecules have a finite volume and there are intermolecular forces between the gas molecules. So at moderately high pressure, PV over RT, high pressure, is less than 1. This is around here. Okay, there are negative deviation observed. The predominant factor in moderately high pressure will be intermolecular attractive forces. So at low pressure, the space between the particles of any real gas are so large that intermolecular attractions are negligible and the gas behave nearly ideally. As you increase the pressure, the gas particles come closer together and the intermolecular forces between the gas particles become significant. But when the gas molecules approaches the wall of the container, nearby molecules attract it, which lessen the force of its impact on the wall. So the effect results in a decreased gas pressure. So, and thus a smaller numerical value in the PV over RT ratio. And hence you will see that how come the PV over RT will drop to below 1 is because of this reason. Okay, so the impact on the wall decreases because of attraction from nearby molecules. But when you have very high pressure, you will see a positive deviation. And the predominant factor will be the size or the volume of the gas particles. So at low pressure, the gas particles are far apart and the empty space between the particles is enormous compared to the volume of the particles themselves. So the free volume is noted as V3, the volume of container V container, and the volume of gas molecules is V gas molecule. So the volume of the gas molecules will be negligible compared to the volume of the container, whereas free volume can be calculated as the volume of the container minus the volume of the gas molecule. Because the gas molecule is so negligible in volume, so the free volume is just the volume of the container, given this is negligible. All right, so that is how we can assume ideality behavior. So at very, very high pressure, right, the molecules now are close together and the empty space between them becomes significantly reduced. Since now the volume of gas molecule is not negligible compared to the volume of container, the free volume is equals to the volume of container minus gas molecule, not equal to volume of container. We continue to use volume of container instead of free volume as the V in the ratio. So the numerical become artificially high because of an increased volume. So it becomes greater than 1. Yeah. Because by right it should be free volume, the volume that is actually used in the ideal gas equation, right? The volume of the gas, but actually we use a container, so it becomes artificially high. So extremely high pressure, right? The space taken up by the particles themselves causes the free volume to be significantly less. So if you continue to use a container volume, the ratio is artificial high and above the ideal value. Now, so this diagram shows the effect of external pressure on molecular attraction and hence measured gas pressure. So at ordinary external pressure, the molecules are too far apart to interact. With increase in pressure, the molecules become close enough to form intermolecular force. And also the attraction will lower the force of collision with walls. Yeah. Whereas, so this is the first part here. Yep. Then we have the next one. So if we have very high pressure, the free volume will be much less than the container volume. But in the equation, we continue to use the volume of container instead of free volume, which explains why the ratio is artificially higher than 1. So if you plot a graph of PV over RT against P for 1 mole of gas at different temperature, this is what we get. So the graph shows that nitrogen will deviate most from ideal behavior at high pressure and low temperature. So it can be seen that the plot, right, shows that the lower the temperature and the higher the pressure, the greater the deviation from ideal behavior. So at high pressure, the nitrogen molecules are much closer together. So the volume occupied by the nitrogen molecules is significant compared to the volume of the container. And the intermolecular forces at high pressure will no longer be negligible. At low temperature, the nitrogen molecules have lower kinetic energy. So they couldn't overcome the intermolecular forces. And hence the intermolecular attractive force become significant. And if we have the comparison between the different gases at the same conditions, we see that, hey, gases with stronger intermolecular forces tend to deviate more. So this is very important. Intermolecular forces have an important role in this. All right. So ammonia form hydrogen bond, which we cover under chemical bonding 1. You can refer to the video on what is hydrogen bonding and why does it result in difference in property. But here we just take note that ammonia form stronger hydrogen bond compared to the weaker ID-ID interactions between hydrogen and nitrogen molecules. And if we compare nitrogen with hydrogen, all right, nitrogen with hydrogen, so for gases which form instantaneous dipole-induced dipole interactions, molecules or atoms with more electrons will form stronger ID-ID interactions and tend to deviate from ideal behavior. Okay, so you can see from the graph that both hydrogen and nitrogen do have ID-ID interactions, but nitrogen has more electrons and hence larger electron cloud for polarization. So nitrogen molecules form stronger ID-ID interactions and will deviate more from ideality. And also nitrogen molecules occupy more space. So the volume of nitrogen molecules will be less negligible than of hydrogen. Okay? More significant. So nitrogen deviate more from ideal behavior compared to hydrogen. Okay? Then, okay. In general, right, deviation is greatest for polar molecules with strong intermolecular forces of attraction and smallest for small non-polar molecules. So the deviation for ammonia will be greater because of this high polarity. Then we have HCl, CO2, O2, N2, H2, etc. Okay. You can see that there is greater deviation, negative deviation for ammonia because of, if you have negative deviation, it's more like intermolecular force. Positive deviation is largely due to size of or volume of gas particles compared to the volume of the container. So that's the reason why there is some difference between the type of deviation seen. Okay. Now, what is partial pressure of gas? So for a mixture of gas that do not react with each other, each gas behaves as if it were only the gas present. So for such a mixture, each gas will exert its own pressure independent of the other gases present. So this is known as partial pressure. Okay, so we are assuming that in this mixture of gases, they do not react with one another. So the pressure of the gas is exerted by each gas, meaning they are independent of each other. So the partial pressure of a gas is the pressure that a gas in a gaseous mixture will exert under the same physical conditions as if it's alone were to occupy this container. So with that, we come up with Dalton's law of partial pressure, which states that, okay, the total pressure of a mixture of non-reacting gases will be the sum of the partial pressure of the individual gases. So we have gas A, gas B, gas C. So if we mix them in the same container, the total pressure will be the sum of the individual pressure, or we call them the partial pressure. Now, the mole fraction of component A is a mixture of the ratio of the number of moles of A to the total number of moles of all components present in the mixture. So mathematically, the mole fraction is equals to the number of moles of component A divided by total number of moles. Then the partial pressure is the product of the mole fraction and the total pressure. So if we want to find the pressure of a gas, we take the number of moles multiplied by the total pressure. Now consider a mixture of non-reacting gases A, B, C in a container of volume V at temperature T. So we assume ideal gas behavior and apply the ideal gas equation. So we have PV equal nRT, PV nRT. So this is like this one is for the total pressure. This one is for the individual gas A. So we divide 2 by 1. I just want to show you like how do we get the equation here, the derivation. So PA over P total cancel off the V because we are considering they are in the same volume of the container. NA over N total cancel off RT, which is equals to the fractional. So you rearrange this equation, you have pressure A equals to NA over N total times P total. So PA is equals to XA, which is the mole fraction, the number of moles of the gas divided by total number of moles of the gases present. And then it applied to gas B and C. And if you add these 3 together, you should get 1. Because fraction, so individual fraction should add up to 1. Okay, let's look at another example. You have a mixture of 1 mole of nitrogen, 2 mole of oxygen, and 2 mole of carbon dioxide that exert a total pressure of 10 atm. So calculate the mole fraction and the partial pressure. So the total amount of gases, which is 5 mole, okay, total pressure was already given as 10 atm. So the mole fraction of nitrogen is just 1 over 5, 0.2, oxygen 2 over 5, CO2 3 over 5 as well. And then the partial pressure of nitrogen will be 0.2, which is 1 over 5, calculated just now, times total pressure, which is 2 atm. Then repeat the same for the rest. All right, so the total pressure here should add up to 10, just to check. And the total fraction should add up to 1. Another example, okay, you have 5 dm³ of flask containing gas X at a pressure of 8 atm is connected to another flask containing gas Y at a pressure of 2 atm, having a volume of 10 dm³ as shown in the diagram on the right. So what is the final pressure in the flask if the valve opens and pressure is allowed to equilibrate? Assuming that these 2 gases, right, do not react and the temperature was constant. Okay, so if you need to understand that when you release the valve, right, okay, the total volume now will be 5 plus 10, because before that, they are separated, 5 and 10 dm³ respectively. So when you release the valve, right, you have to total out the volume to be 15. So let's look at the first method on the left. How do we approach this question to find the final pressure? Now, let's make final pressure be P final. Just use ideal gas behavior. Ideal gas equation to assume ideal gas behavior. you can do that actually by writing this statement, totally fine. And then the P final equals to times V equals to nRT, n total. So you split up nx plus ny, then you just is equals to nRT plus nRT x and y respectively, which is the same as PV plus PV. So this is nRT equal to PV. So you just equate these two, and this is the equation. And then you just, because you still need to relate to the individual pressure and volume. So I cannot just put as nRT because I do not know the temperature. I do not know the number of moles. I know R, but I don't know N and T. So I need to equate them to another variable that I can relate to. I need to use variables that have values given. So I have 8 ATM and 5. You use this, and you have used this also. Just add up. You get 60. Then divide by this 15, the total volume, I get 4 ATM. So that's for method 1. Then for method 2, right, you can use partial pressure method. So let X and Y be Px and Py respectively. Since temperature and amount of gas is constant, the Boyles law can be applied. P1, V1 equal P2, V2. So for gas X, right, you just take Px times 15 equals to 8 times 5 because the pressure was 8, right? Then you have 40. And then you divide by 15, you get 2.67 ATM. Okay, so this 15 is the total volume because now the gases, right, are moving constantly and randomly. So the gas X is not just restricted to the 5 dm cube. It's now occupying a space of 15. So it can roam around in the 15 dm cube. Therefore, the new volume was 15. Okay, because the gases are moving within this 15 dm cube and not just restricted to 5. And with increase in volume, of course, the pressure will decrease. I'm talking about partial pressure. So repeat the same thing for gas Y, okay? And we will have 1.33. So you just add up the pressure, assuming, yeah, sum of partial pressure equal to pressure Y. You also can get the answer. Now, what is vapor pressure? Now, we consider a system where the liquid is enclosed in a closed container. So what happens is that some of the more energetic particles on the surface of the liquid possess sufficient energy to escape from the attractive forces holding liquid together. In other words, they evaporate. So evaporation is a process where the particles on the surface of the liquid gain enough energy to escape. And they escape by overcoming the attractive force that hold them. So in a container of liquid, right, there is always constant evaporation. But in a closed container, right, somehow they are trapped in the space. They cannot release. So because they cannot get released, right, so the pressure exerted by the gaseous particles on the liquid surface, right, so they will exert pressure because they are just here. So they will exert pressure on the liquid surface. So this pressure, right, is called vapor pressure. And they're also exerting on the walls of container. So it's related to how much gas particles are there. The more, then the higher pressure. So there'll be a dynamic equilibrium set up where the number of particles leaving the surface is exactly by the number that rejoin. So particles may come out and come down, you know? So there's this equilibrium. There's this change happening. The particles evaporate and then they go back, rejoin back to the liquid. So there will be a fixed number of gaseous particles in the space above the liquid, but there's still a dynamic equilibrium set up. So when equilibrium is established at a particular temperature, the vapor pressure is known as standard vapor pressure. Okay, just for your knowledge, and we go on. Now, boiling occurs, right, when the saturated vapor pressure becomes equal to the external pressure exerted on the liquid. Okay? The boiling point of a liquid gives an indication of the strength of its intermolecular force. So the stronger the intermolecular force, the higher its boiling point. So for a liquid with strong intermolecular forces, it will be very difficult for the particle to escape from the surface. So this translates to lower saturated vapor pressure and lower volatility. So we can make this connection. The stronger the intermolecular forces, the lower its volatility and saturated vapor pressure, but the higher its boiling point. Okay, so when the saturated vapor pressure becomes lower, then it will be more difficult to boil, right? Yeah. And boiling occurs when this saturated vapor pressure becomes equal to the external pressure exerted on the liquid. That's where if the, yes, so at this point, right, the liquid can boil. Okay, now that's enough. So let's look at this example. Consider the 5 alkanes. Which property of the alkane does the numerical value decreases? So for which property? So the answer will be D. Why? So the vapor pressure actually decreases. All right, because it's not A, B, and C. Yeah. For C, it's definitely out because with increased molecular mass, the intermolecular forces become stronger, more energy required to overcome. So the boiling point should increase. As for strength, intermolecular force doesn't make sense, also increase, right? As for density, it also increase. But vapor pressure means that it becomes harder for molecules to escape. So it makes sense, which means higher boiling point. All right. Now, as the size of alkanes increase from left to right, the number of electrons increase, and this causes the electron cloud to become more polarizable. And there's increased strength of IDID between molecules. So B is definitely wrong. Since the strength of IDID increases, molecules are held closer together. So with that, right, the molecules are actually packed closer together within the same volume. This results in an increase in density. So A is also wrong. Now, when the strength of intermolecular forces increases, boiling point will increase. So C is wrong. Now, so only D will be correct because with stronger IDID between alkanes, it will be harder for molecules to escape from a liquid surface. This is causing the vapor pressure to decrease. So before we end the session, just look through the summary of gas law. So we talk about how different gas law like Boyles Law, Charles Law, etc. form the ideal gas law, and make sure you know how to draw or sketch the graphical representations for the different graph as we have mentioned. And that's about it, and all the important information about Dalton's law, how to apply it, etc. I hope you benefit as much, and please do subscribe to my channel if you're not done so to get latest update of the videos. Thank you.